Hello, my name is Desmond Edagese, and I'm here to take us on the subject mathematics. Today, we'll be looking at the theme numbers and numeration, and under numbers and numeration, we'll be learning all about sets. Our topic for today under sets is Venn diagrams. What are Venn diagrams? Venn diagrams are diagrams that are used to better illustrate set relationships. So imagine all the relationships we've learned so far in sets. We have relationships like union, intersection, difference. We also learned about operations like complement. Subsets was also a concept that we learned in sets. Well, Venn diagram is a diagram that helps us to better illustrate all of these operations in a way that is clearly understandable. So it helps us visualize these sets better. Basically, to draw a Venn diagram, you first draw a rectangle, which is called your universe. In our classes before now, we learned that the universe is the set that contains all the elements in a set of given problem. In the context of Venn diagrams, the universe is basically everything we are dealing with right now in the given problem. The member sets, which are all subsets of the universe, are also illustrated as circles within our rectangle, which is our universe. Let's go on to see what a typical Venn diagram looks like. We said that the Venn diagram is drawn by drawing a rectangle. The rectangle we see here is the universe. And we said the universe is the set that contains all the elements under consideration. So this is a Venn diagram of the operation, the complement of A, or what we call A complement. The set A is drawn within our rectangle as a circle. The shaded portion is the area under our consideration. The shaded portion depicts the elements that are within our universal set, which is our rectangle, that are not in our given set A. So the shaded portion is the area of our complement, the complement of A. This is another Venn diagram that depicts the operation of A union B. Again, we have our universal set, which is the rectangle, and we have our set A, which is our circle drawn here. We also have a set B, which is a second circle drawn. Our set A and B are within our universal set, that is, within the borders of our rectangle, which represents the universal set. The operation A union B is illustrated here by the shaded parts. A union B is the elements that are all present in A and also in B. So we have A union B illustrated by our shaded areas. Let's take a look at another Venn diagram. The Venn diagram here also is depicting an operation of A union B prime. That is the complement of the union A and B. Once again, our universal set is drawn as a rectangle that encloses every other set under consideration. The set A is drawn as a circle all within our rectangle, while our set B here is also drawn as a circle also within our rectangle, which is our universal set. A union B is the union of A and B, that is the elements present in A and also in B. But that is not what we seek for in our operation. We are seeking for the complement of A union B. The complement, therefore, is all the elements that are present in the universal set but not present in the union of A and B. And our shaded portion here is that area under consideration. It is the elements present in the universal set but not present in our union A and B. So we see that A and B, the region represented by our circles, are unshaded, while our shaded parts depicts the complement of the union A and B. Let's take a look at the second example we have here. This is the Venn diagram of the operation A intersection B. Again, we have our rectangle that represents our universal set. Universal set is the set of every element under consideration in our given set A and B. Our member sets A and B are members of our universal set, and A is represented as a circle. B is also represented as another circle. The operator here, which is our intersection, is depicted by the intersection between both circles A and B. That intersection is further shown by our shading here. The shaded portion is the intersection between A and B. Let's take a look at another example. We also have another Venn diagram here that depicts the operation we have here, which is the B complement, or the complement of the set B. We said the complement of a set is all of the elements within the universal set that are not in the given set. In this case, B is our given set. We have a set A also there. Therefore, the complement of our set B is all of our universal set, and that is our shaded portion under consideration here, with the exception of the given set B. So our set B remains unshaded, while every other area within our universal set is shaded, and these shaded areas represent the complement of B. Let's take a look at another Venn diagram. We have our universal set again, which is our rectangle here that encloses every set under consideration. Our sets under consideration here are set A and B. So we have two circles to represent each set A and set B. Our given operator here is the difference. So we have to find A minus B. A here minus B would be the shaded portion here, which is the part of our circle that contains all elements in A that are not in B. So our shaded portion here represents all elements that are in A but not found in B. Let's also take a look at our other example here. We also have a Venn diagram that depicts this relation here of A minus B, all enclosed in the bracket prime. So we have A minus B. First we have A, which is represented with a circle, and we have our set B also represented with another circle. Remember, we said in the example before now that the shaded portion of A minus B would be this portion here. But what we seek for, or what is the area under consideration here, is the complement of A minus B. So A minus B is all of our portion here. And we're looking for the complement of A minus B. The complement, therefore, of this portion would be every other portion under our universal set that is not inclusive of this portion. That is, every element of the universal set that is not an element within the portion that we've drawn here. And therefore, we have the shaded portion that is all of this part of our universal set that is not a part of the shaded portion. That is our operator A minus B prime. Let's take a look at another Venn diagram. We have the Venn diagram of A is a proper subset of B, all enclosed in brackets prime. That is the complement of A subset B, proper subset in this case. For A to be a proper subset of B, it means that A is enclosed in B, or B contains A. Let's see our diagram here. We have the set A and we have the set B. From our diagram, we see that A is truly enclosed or contained inside the set B. But what we seek for is the complement of A, that is the proper subset of B. And that means every part that is beyond our part indicated here, that is all the elements of our subset, that is not an element of the set A. And that is indicated by all the shaded regions here, with the exception of the inner parts of our set A. So our Venn diagram here depicts the relationship, the complement of A subset, proper subset B. Let's take a look at another Venn diagram. Once again, we have a Venn diagram with our universal set being the rectangle that encloses every other given set in consideration. We have two sets in consideration, and that's set A and a set B. Our operation here says the complement of A intersection B. A intersection B would be this portion here, that is the intersection between our set A and B, which is also the intersection between each of the circles that cross each other. The complement, therefore, would be every area that is outside of our indicated area here. And that would be every element under consideration in our universal set that is not an element of the intercept between A and B. To further illustrate this relationship, we would shade the area that is required under consideration. It is all of this area shaded, with the exception of the area not shaded. And that is the Venn diagram of our relationship, the complement of A intersection B. Now let's take a look at some practical examples. If we have a universal set with elements 1, 2, 3, and 4, and we have A, which is a member element of our universal set. A is the set that has elements 2 and 3. A is a subset of our universal set here. We've been asked to draw the Venn diagram 1 and hence find the complement of A. To draw the Venn diagram, we'll quickly draw our rectangle, which is used to illustrate our universal set. Our universal set contains the elements 1, 2, 3, and 4. But within our universal set, we have our set A, which is a subset of our universal set that has elements 1, 2, 3, 4. Set A has elements 2 and 3. To draw our member set A, we'll simply draw a circle and indicate its elements within the circle. So we have 2 and 3. But remember that our universal set has elements 1, 2, 3, and 4. And we have just one member set. It means, therefore, that 1 and 4, which are elements of the universal set not found in our given set A, would be written outside of the borders of our set A. So we write 1 outside of the border, but still within the range of our universal set. We also write 4, which is also not found in our given set A, but is a member of the set of our universal set. Now we've been asked to find the complement of A. The complement of A is the elements found within the universal set that are not found in the given set A. And those elements are 1 and 4. Therefore, we say the complement of A is the set that has elements 1 and 4. Let's take a look at another example. If we have a universal set given that has elements A, E, I, O, and U, if A and B are also given to us, where A has elements A and I, and set B has elements E and U, to draw our Venn diagram with the information given to us, we'll first draw our rectangle, which denotes our universal set. Next, we'll draw our member set A. We said every member set is a circle, so we draw our circle and write the elements of our set within our circle. We have A and I as the elements of set A, so we write A and I within the confines of our circle. Next, we also draw our circle B, taking note that our circles A and B will be depicted as disjoint sets as indicated in our problem. If they are disjoint sets, it means that they have no set in common, so there is no intersection. Hence we have our circles separated with no form of contact between both circles. Our set B has elements E and U, so they are written within our circle. Let's take a look again at the members of our universal set. We have A, E, I, O, and U. Set A has A and I, while B has E and U. Notice that our element O cannot be found in either set A or set B. Hence it is found outside of the borders of both circles. So we write our element O outside of the borders of both circles, but still within the borders of our universal set. Next, we succeeded in drawing our Venn diagram. Let's find A intersection B. A intersection B would be the intersection that is similar elements found within A and B would be listed. We've already said that the sets are disjoint sets as indicated from our question. It means that our circles drawn would have no form of contact. Therefore, there is no intersection between set A and set B. It means that the intercept of A and B would give us a null set or an empty set. And that's our answer. Let's also take another example. If we have a universal set that has sets 1, 2, 3, 4, 5, 6, and 7, and we are given two sets A and B. Set A has elements 2, 4, 6, and 5, while set B has elements 1, 2, 3, and 5. With this information, let's quickly draw our Venn diagram. First, we'll draw our rectangle to depict our universal set. Next, we draw our member set A, which is depicted as a circle. We also draw our member set B, which is also depicted as a circle. The elements of A are written within the boundaries of our circle. So A has elements 2, 4, 6, and 5, while B has elements 1, 2, 3, and 5. From the elements listed for A and B, if we take a quick look, we'll find that we have intercepts. We have common elements. 2 is a common element between both sets. And also notice that 5 is a common element. It means that when we draw our circles within the Venn diagram, we would intercept both circles like so. And within that portion that is the intercept, we'll write our common members. There are 2 and 5. Meanwhile, the other elements for our set A are 4 and 6, so we write them also all within our circles. So if we took our circle A alone, we would have our elements listed as 4, 6, 2, and 5. Let's do same for B. B has elements 1, 2, 3, and 5. We already have 2 and 5 as our intercept. The other elements left are 1 and 3, so we write them down within the boundaries of our set B. If we also took careful look at our set B only, we'll also see that we've listed all our elements 1, 2, 3, and 5. 1, 2, 3, and 5. So we have a Venn diagram, and we can easily get our solution here. We've been asked to find the intercept between A and B. The intercept of our set A and B is the intercept of our circles drawn within the Venn diagram, where we have 2 and 5. Therefore, A intersect B would give us the set that has elements 2 and 5. Let's take a look at another example. If we have the universal set that has elements 1, 3, 5, 7, and 9, and A is given as the set that has element 3 and 5, while B is the set of elements 1, 3, and 5. We've been asked to draw the Venn diagram of the arrangement. First, we'll draw our rectangle to depict the universal set. And within the borders of a universal set, we'll draw our member sets A and B. First, if we noticed, we'll find that the elements of A are 3 and 5, while the elements of B are 1, 3, and 5. It means that all of A can be found inside of B. That means that A is a subset of B. In other words, B contains A, or A is contained in B. If we draw our circle here to depict the set A, we'll draw it inside of the other circle, which is B. This circle within a circle indicates that A is a subset of B, or B contains A, or A is contained in B. Take note also that the set A is not just the subset of B, but it is a proper subset. A proper subset has at least one element that is, in this case in B, that is not in A. While all of A can be found in B, at least one element in B cannot be found in A. That element in B that cannot be found in A is 1. Therefore, 1 is written within the borders of B, but outside of the borders of A. And so we have 1 here. Next, let's take a look again at the elements of our universal set. It has elements 1, 3, 5, 7, and 9. The elements of A and B listed are 1, 3, and 5. So we have 1, 3, and 5. If we crossed that out, we have 2 elements that are in the universal set, but not in any of our given set A or B. Therefore, we write them outside of the boundaries of A or B, but within the boundaries of a universal set. Hence, we have 7 here, and we have 9 here. And that is the Venn diagram of our arrangement. Again, A is the proper subset of B, while B is the proper subset of the universal set. All of B is the proper subset of the universal set, since there are elements of the universal set 7 and 9 that cannot be found in B. Now we've learned about how to make use of the Venn diagram for different scenarios of set operation. Let's see if we can carry out some exercises to see how much we've understood so far. If we were given a universal set to be the set that has elements A, B, C, D, E, F, G, H, I, and J, and we have set A with elements A, B, C, D, F, and set B has elements D, F, E, and G, we've been asked to draw the Venn diagram and hence use the Venn diagram to find A union B, A intersection B, the complement of A, the difference B minus A, the complement of the intersection A and B, and the complement of the union A and B. First, let's go ahead to draw our Venn diagram. By drawing our rectangle, our rectangle would enclose 2 member sets, A and B. We said that each member set is depicted by a circle drawn within the rectangle, which is the borders of our universal set. So let's draw a circle to depict our set A. We'll also draw another circle to depict our set B. But first, we must know how our circle will be drawn within our rectangle. Would it intersect our circle A, or would it be separate? We determine that fact by looking at the members of our set A and the set B. If there is an intercept of its membership, then we depict that as circles that have a path that come together or intersect in our Venn diagram. So let's quickly find out if we have similar or common elements between sets A and B. So we have set A as A, B, C, D, and F, while B has elements D, F, E, and G. We have common elements, and those are D and F. Therefore, we will draw now our circle for the set B to intercept our set A at this point. This region would contain the common elements that we have between A and B, and that's D and F. With what we have so far, we can now write out the remaining elements of our sets A and B within the confines of each circles. Let's take A first. A has elements A, B, C, D, and F. D and F have already been put down as common elements of A and B. So we'll put down our other elements A, B, and C within the confines of our circle A, B, and C. We'll also do same for our set B. We've already put down the common elements D and F, so we'll put down the remaining elements E and G within the confines of our circle B. Let's quickly take a look again at our circle A. All of this region is our circle A, and we do a quick check to confirm that every element is present. So we have elements A, B, C, D, and F. We have A, B, C, D, and F. Let's do the same check for our circle B. All of this region is our circle B. Again, we have elements of the set B as D, F, E, and G. We have D, F, E, and G. Well, so far we have our Venn diagram in place, and though we are still in progress, we are almost done. Next, let's take a look at the elements of our universal set. It has A, B, C, D, E, F, G, H, I, J as its elements. If we take a look at the elements listed so far in our set A and B, we have A, B, C, D, E, F, and G. It means therefore that the elements H, I, and J that are elements of our universal set are not found in the set A and B. Therefore, since they are found within the confines of our universal set, but not in A or B, they will be written outside of the borders of our sets A and B. So we'll write down H at any point within the borders of our rectangle, but outside of the borders of our circles. So now we have a Venn diagram that is complete, and we can use this Venn diagram to answer all of our questions. Now let's begin with our first question here. A union B. A union B would be the region or the part of the set A and B that has every element listed. That is, the elements of A combined with the elements of B. So we have our region here, our region here, and our region here. The region colored yellow is the region of our union A union B. That region contains the elements. Let's quickly take a look. We have element A, we have element B, we have element C, we have element D, we have element F, we have element E, and we have element G. So A union B is the set that has elements A, B, C, D, E, F, and G. Let's take a look at our second question here. We've been asked to find A intersection B. So we have our intercept at this point. That is the part of our Venn diagram that contains similar or common elements between A and B. If we take a look at that region, we have elements within that region, and they are D and F. So the intersection of A and B is the set of elements D and F. Let's take a look again at the next question we have, which is the complement of A. The complement of A. The complement of A, we said, is the set of all elements that are in the universe but are not in our given set, which in this instance is A. That part that is the complement of A would be this region, this region. The shaded region again indicates all of our region that is within the universal set but is not in our given set A. So once again, if we take a look at the elements within our colored region, we would have those elements as E, G, J, H, and I. So again, the complement of our given set A is a set that has elements E, G, J, H, and I. Let's take a go at our next question here. We've been asked to find the difference, that is B minus A. B minus A. B minus A is a set that has the elements that are all in B but not in A. So we have our region B here minus A. This region indicates all of B and none of A. That is, even the common elements that were between A and B is exclusive of our colored region. So B minus A contains those elements that are only found in B and not in A at all. If we looked at a list of the elements within our colored region here, we'd have just two elements, E and G. And that is the difference, B minus A. Let's also take a go again at our fifth question here. It says the complement of A intersection B. So let's try and find that. The complement of A intersection B. A intersection B normally would be this region here, which is the region or the set that contains common elements between set A and set B. But what we seek for is the complement of A intersection B. The complement, therefore, is all of the elements within our universal set that are not found within our region here, which is the intersection A intersection B. Therefore, to indicate the region in question, would have all of this region, exclusive of our intercept A and B, which is our region here. Therefore, the elements found in all of our colored region here, if we listed them, would be A, B, C, E, G, H, I, and J. And that's the complement of A intersection B. Let's take a go at our last question here. We've been asked to find A union B, the complement of A union B. Again, A union B is the region in our Venn diagram that contains elements both present in A and also present in B. That is, all elements found in A in combination with elements also found in B. That element would be this region indicated here, or those elements will be found in our region that is a combination of both circles, stands for our set A and B. It means therefore that the complement of our union A and B would be every region within the Venn diagram that is the region under the universal set, but not in the region of A and B. So we'll simply have this region here as the complement of the union A and B. Again, we said that region is all of the region under the universal set that is not in the region of the union A and B. Hence, we see A and B as clear as possible without a coloring. If we quickly put down all the elements found in our colored region, would have three elements, that is H, I, and J. Therefore, A union B prime, that is the complement of A union B, is the set that has elements H, I, and J. And there we have our answer. So far, we've learned how to use the Venn diagrams to illustrate set operations like union, intersections, complement, subsets, and the likes in a manner that clarifies and simplifies them. Well, the use of this knowledge, along with the use of Venn diagrams as a means of illustration, can be applied in real-life situations to store all kinds of numerical information, and hence we may use our knowledge to solve the problems that arise from such data. We'll go into some examples now to see how Venn diagrams and the use of our set operations can be applied in real-life problems. Let's take a typical situation like this. In a village where all the people speak Hausa or English or both, if 97% speak Hausa and 64% speak English, what percentage of the villagers speak both languages? First, we know that everyone in the village would be 100%. So we represent our universal set as 100%. The percentage of persons in the village that speak Hausa, let's represent with the letter H, and that of course is 97%. The percentage of villagers that speak English would represent with the letter E, and they are 64%. The percentage of persons that speak both languages would be therefore the intersection between those that speak Hausa and those that speak English. Our cardinality would be represented here as X. We have our information that we can illustrate with a Venn diagram. Let's go ahead and do that. The Venn diagram again would represent our universal set that encloses our member sets, which are H and E. So H, representing the villagers that speak Hausa, would be our circle here, while our circle here, E, represents the villagers that speak English. Let's take a look at our information here. We said that 97% speak Hausa. It means that our region here would have 97 within its border. While 64% speak English, it also means that our region here would have 64 within its border. But we also said that there is a percentage that speak both languages, and that is what we are trying to find in our question. We represent that as the intersect between our both sets, and X is our unknown, so we have X within that border or that region. Next, consider that the percentage that speak Hausa was 97, and this is all the region of that percentage. It therefore means that our region here would be 97 minus X. For our percentage of persons that speak English, this region would also be 64, which is the percentage of all that speak English, minus those that speak both English and Hausa, and that would be the region here, 64 minus X. So we have our information. The intercept therefore would be our shaded part here. That is H intercept E prime. The next region under consideration would be this region here, which is the intersection between our set H and our set E. That region has X, which is the unknown that we seek for. So we have our region here, which is the intersection between H and E. The last region under consideration here is our region here. That region in set terms is the intersection between E and H prime. H prime being the complement of H here, which is the region under the universal set that is not within the borders of our set H. The intersection between E and that region is our shaded part here. So we have the summation of all of this to give us our universal set 100. The values that we have within those borders are 97 minus x for the cardinality of H intersection E prime. We also have x for the cardinality of our intersection here, H intersection E. Then we have 64 minus x for the cardinality of E intersection H prime. All of this summed up would give us 100. We'd have 161 minus x to give us 100. 161 minus 100 would give us our value x. And that is what? 61%. It means that the percentage of those that speak both languages is what? 61%. Now let's try some exercises of our own. Let's take this exercise. If 20 people apply for a job, 12 have school certificates and 10 have diplomas. If 2 have no qualifications, how many have both a school certificate and a diploma? Once again, from the example we did earlier, we can easily have our solution. Let our universal set be the set of everyone applying for a job. We have 20 persons applying. Let S also represent the number of persons that have school certs. The set of persons with school certs. Let D represent the people with diploma. We are required to find the cardinality of the intersection between S and D here. That is the number of persons that have both school cert and diploma. That will be the intersection between our set S and our set D. This is what we are required to find. Let's quickly draw our Venn diagram from the information we have so far. So again, we'll draw a rectangle to represent our universal set. We'll draw our member sets within our Venn diagram. We have our set S and our set D. From the information we have an intersection which is our unknown as X. So we write X in this region of the intersection of our circles. Also, our set X we have gotten from our question is 12. That is, 12 people have school certificates. It means that all the region under consideration as our set X is 12. It also means that this region here would be 12 minus X. For our set D, we also have this region to be the number of persons that have diploma, which is 10, minus those that have both diploma and certificate. Lastly, we have 2 persons that have no qualifications. Such persons will be outside of our borders S and D, set S and D, sorry. Such persons will still be within the border of our universal set, but not in the borders of our sets S and D. So we have our Venn diagram completely drawn. Let's go on to solve our problem. Now, since the cardinality of our universal set is 20, the cardinality of the set S intersection D prime is 12 minus X. That is this region here. this region is the intersection of our set X and the complement of D, which is all of this region outside of this region. That intersection is our shaded region here. 12 minus X. Also, the cardinality of S intersection D, which is this region here, which is the number of persons that have both certificate and diploma, is the unknown that we look for, and that's X. Next, the cardinality of our region here is S prime intersection D. That is the complement of S, which is all of this region outside of this region X, and the intersection of this portion D would give us this portion. So we'll have that as 10 minus X as indicated on our Venn diagram. And lastly, we have the cardinality of S union D, which is the union of every member set here, prime. S union D prime is the complement of the union S and D, and that is the region outside of the union but still within the range of our universal set. That value we get is 2. Therefore, every region under our universal set here would be equal to 20, which is the total number of persons that applied for the job. But we would add up this region with this region and of course our region here. Let's do that quickly. We would have the cardinality of S intersection D prime plus the cardinality of S intersection D plus the cardinality of S prime intersection D plus the cardinality of S union D prime. This would give us 12 minus X plus 10 minus X plus 2, which is equal to our universal set 20. That would give us 12 plus 10 plus 2 minus X plus X minus X, and that would give us 20. Of course, minus X and plus X would cancel out. I would have 12 and 10 and 2 as 24 minus X is equal to 20. X therefore would be 24 minus 20, and that would give us 4. So we have 4 persons, which is the value for X, that have both certificate and diploma. Let's take another exercise. In a class of 35 students, 19 take history and 12 take economics. If 5 persons take both subjects, how many take neither? To do that, again we'll say let our universal set be the number of students in our class, which is 35 persons. Let H be the set of students who take history. Let E be the set of students who take economics. it is required for us to find how many students take neither. That is the intersection of H union E prime. That is the complement of H union E. Let's draw a Venn diagram with the information that we have so far. So once again, we represent our universal set with the rectangle. The universal set contains our member sets H and E. So let's represent H with our circle here and represent E also with our circle here. We said that H is the number of students that take history. 19 students, as indicated from our question here, take history, while 12 students take economics. 5 take both subjects. 5 students that take both subjects here would be the intersection between our set H and E. And we will indicate that in our Venn diagram here as the intersection between both circles. So we have 5 in our Venn diagram put down there. This region is the intersection between our set H and our set E. If we consider our region here, which is all of the set H, we have 19 students to put down in this region. But remember that 5 students take both economics and history. It therefore means that this region left over will be 19 minus 5. And of course that would give us what? 14. So we have 14 students under this category. Let's also consider the region for economics. In total, 12 students take economics. But remember again, 5 take both history and economics. It therefore means that this region left over would be 12 minus 5 students, which would give us 7. So we have 7 students in this region. Finally, we have a set of students that take neither of the courses. That category of students that take neither of the subjects will be indicated outside of the borders of those that take history and economics, but still within the border of our universal set. So we could write that as X, which is our unknown. To go on, we say since the cardinality of our universal set, that is the total number of students, is 35, the cardinality of H intersection E prime, that is the complement of E, is 14. That is this region here is H intersection E prime. Also, we know that the cardinality of H intersection E, that is the number of students that take both history and economics, as 5. We also know that the cardinality of E intersection H prime is 7. And that is this region here is E intersection H prime. The last region that we have is the cardinality of H union E prime. And that is the region that is under the universal set, but not within the borders of both our history or English class. These are the categories of students that take neither of the courses. Therefore, the total region under consideration, which is the totality of our universal set, would be the cardinality of H intersection E prime plus the cardinality of H intersection E plus the cardinality of E intersection H prime plus the cardinality of H union E prime. That is our region here, which is H intersection E prime. Our region here, which is H intersection E. Our region here, which is E intersection H prime. And our region here, which is H union E prime. If we add all of that, we have values 14 from our region here, plus 5 from our region here, plus 7 from our region here, plus x from our region here, to give us 35. X would therefore be 35 minus 14 and 5 is 19. 19 and 7 is 26. We would have 9 as our answer. It means that the number of students that take neither economics or history is 9. And that's our answer. Let's also take this other example here. If we have 50 students questioned on what their favorite sport is, 16 said basketball, 41 said football, 7 said they like neither. How many liked both sports? Again, let's remember our steps. First, we say let our universal set, which is the total number of students under consideration here, let that be 50. Let B represent the set of students who like basketball. And let F be the set of students who like football. It is required that we find the cardinality of the intersection between our set B and F. Let that be our unknown. That is, how many like both sports? We have information enough for us to draw a Venn diagram. Let's go ahead and do that. So again, we draw a Venn diagram as a rectangle that is the universal set. Our rectangle contains our member sets B and F. So we have our member set represented as circles. The number of students that like basketball is 16, while the number of students that like football is 41. It means that the region of our circle here for B, which stands for the students who like basketball, would have 41 within its borders. But remember that 7 are said to like neither sports. Neither would mean that they would be outside of the borders of both the set that represent basketball and that represents football, but still within the borders of our universal set. And so we write 7 outside of our borders here. The region that we seek for is the region that like both sports, and that would be the intersection between those that like basketball and football. that region is represented on our Venn diagram as X, which is our unknown. Those that like basketball, therefore, would be 16 minus X. And those that like football, exclusive of those that like both football and basketball, will be 41 minus X. So we have our Venn diagram. If you take a careful look, we have 4 regions. We have the region of those that like basketball alone, exclusive of those that like both basketball and football. We have those that like both basketball and football. We have those that like football alone, exclusive of those that like both football and basketball. And we have those that like neither. Since we know the cardinality of each region, let's take our first region here. It's B intersection F prime. We know that as 16 minus X. We also know the cardinality of this region here as B prime intersection F, which is 41 minus 6. So we have this region, which is B prime intersection F. We know also the cardinality of our region under consideration here, which is B intersection F, to be X. It's the unknown that we seek for. And lastly, we have our region here, which is, we know the cardinality of that region as B union F prime. That is the complement of B union F, which is the set of all our universal sets that is not in the region B and F. And that we have as 7. We have all of these values, and we'll therefore find all the regions as the region under our universal set. Remember, we have 50 students, like we said earlier, representing our universal set. So we do a summation of all our region to have the cardinality of B intersection F prime plus the cardinality of B prime intersection F plus the cardinality of B intersection F plus the cardinality of B union F prime. If we put in their values, we would have 16 minus X plus 41 minus X plus X plus 7 to give us 50, which is our universal set. Quickly, minus X and plus X would cancel out. Would have 16 plus 41 plus 7 minus X to give us 50. And we'll have 64 minus X would give us 50. It means therefore that X is equals to 64 minus 50. And of course, that is 14. So we have 14 students that like both sports. And that's our answer. So in summary, we've learned today that a Venn diagram is a diagram that represents mathematical sets pictorially as circles, all within an enclosing rectangle. That rectangle we refer to as the universal set. We also learned that we use Venn diagrams to better illustrate set relationships like subsets, unions, intersections, differences, complements, and the likes. And finally, we learned that Venn diagrams are also very useful in storing all kinds of numerical information, and hence we may also use them to solve problems that arise from such data. I guess you've learned quite a lot. It was a pleasure for me taking you in this class, and I certainly look forward to seeing you in our next class. From me, it's bye for now. Thank you.